Okay, I hope now it is a bit clear about the different types of braking. So, we have seen this in detail. Having done that, we will just examine what kind of breakers you could see under different conditions. For example, off Bay of Bengal, maybe southeast coast of India, the kind of breakers you would see may be completely different from the type of breakers you would see somewhere near off Bombay. So, this depends, as I have earlier explained, basically on 3 parameters I would say, that is the beach slope and then wave height and the wave period or wavelength. So, the parameter which we had defined earlier is N1, and N1 is the ratio of the beach slope and the square root of the wave steepness. So, if you look at this table, what we have done here is we have assumed the deep water wave height as 1 to 10 meters in intervals of 1 meter, and we have assumed the beach slope here tan beta in orange color, as you can see here, from 0.01 to 0.1 in steps of 0.01, and then here the green color, the values given here is the variation that we have, the values that we have adopted for the deep water wave steepness. So, from this we are trying to obtain the value of n, as you can see in this. So, you see this blue color spread all over gives that the waves are going to be, the breaking of waves would be mostly the spilling type, and try to recollect the definition of spilling type of breakers. So, you see that there is a wide range of wave heights and beach slopes for which the breaking will be spilling. So, in general you can say spilling is most frequently occurring compared to the other, and even plunging to some extent. So, the plunging breakers, if you see, that is marked in yellow, and this is more or less the transition between your spilling and plunging type of breakers. So, for a given site, if you have the wave characteristics, you can very easily examine what kind of breakers you can anticipate at that particular site. So, here we have varied the deep water wave height from 1 to 10 meters, but you can also have deep water wave heights less than 1 meter. So, let us examine what is how the variation would look like for wave heights less than, the wave steepness less than 0.1 meter. So, for example, here in the next, in this slide you see that we have varied the deep water wave height from 0.1 meters, 0.1 meter to 1 meter in intervals of 0.1 meter, and then you look at the variation of your n value that categorizes the different types of breaking of waves. Now, you see from this table that we do have a few points, the conditions under which you can have the surging type of breakers. Surging type of breakers, you should, I am sure you will be in a position to recollect, surging break of it type of breakers will occur over steep slopes. Very seldom you would not see them because normally the tendency is we normally go to beaches where the beach slope is quite flat. So you, for example, if you go to Goa where the beach is quite flat, then you can walk quite a long distance inside the ocean and you will be experiencing kind of spilling type of breakers. And off southeast coast of India, for example Chennai, where you have the major harbour etc., in that vicinity you will be able to see plunging type of breakers occurring more frequently. So here for certain conditions as we have shown here 0.01 and 0.1 for the beach slope, and for very low wave height you see that you can have your surging type of breakers. What does the results indicate? The results indicate from the above table you can see that the parameter N1 that categorize the types of breakers increases with an increase in the beach slope or the seabed slope and decreases with an increase in wave steepness. So this certainly matches with what we have earlier seen, that for flat beaches the type of breakers you will experience is the spilling type of breakers, and for steep slope you would have surging type of breakers, and in between you should have plunging type of breakers. So this table helps us to understand more clearly these two tables. So I suggest you have a critical look at these tables, try to understand what could be the wave characteristics. Suppose if you are located along a beach where the beach slope is of certain order of magnitude which is indicated, try to look at the table and try to go and examine yourself whether what kind of breakers you have. Now apart from the three widely classified breakers, there is yet another breaker which is not that popular, and that is called as collapsing type of breakers. All these breakers actually they have been examined through laboratory investigations. The characteristics of these kind of breakers have been verified or have been understood or studied only through critical laboratory investigations, a detailed one. So they have examined, while doing so they have also found out another type of breakers, and this collapsing breaker is found to be in between plunging and surging breakers. For this type the crest never fully breaks, okay. So the crest will be more or less looking stable. The bottom face of the wave becomes steeper, that is the bottom portion of the wave becomes steeper, and that is before it really collapses, and when it collapses it generates a lot of foam. So now surging and collapsing, as we have seen, are mostly due to steep waves propagating over steep slopes. So in such case we can term or we can call such kind of beaches where you have this kind of two kinds of breakers, namely the surging and collapsing, as reflective beaches. So I hope that you have been exposed now on the details of the wave deformation and also on wave breaking, the conditions of wave breaking etc., and also now categorization of your different wave breakers. Another kind of classification that has been used widely in literature, apart from the parameter N1 and N2, are shown here in this slide. So, we have the parameter here in terms of the deep water wave steepness and tan beta, tan 2 beta and tan beta, and the classification is given here as spilling, plunging and surging, and their range are shown here 0.09 for this parameter, and in this case it should be 0.00048, and these are all obtained from based on only experimental investigations. So, naturally it cannot be holding, it will not hold good for all kinds of beaches, etc. For the slopes which have been adopted, that is 0.05, 0.1 and 0.2. For a few other slopes also you do have some information, but this should be good enough as a broad guideline. So, that shows the that explains the complete description of the spilling, plunging and surging type of breakers. We had earlier looked at the different criteria for the waves to break, and we also saw that the waves can break not only in shallow waters, but also in deep waters. Waves break in shallow waters because we see every time we go to the shallow waters we see the waves breaking, and there are certain conditions or criteria for a wave to break, which I had earlier explained as the depth limited criteria, which will take place in the shallower waters, or the steepness limited criteria in the case of deep waters. There are several formulas available in literature apart from the criteria which we have seen. For example, McCown, his relationship is widely used. What is a breaking wave height? If you ask, it can be easily said that it is equal to approximately 0.78 times the water depth. This 0.78 is a kind of an empirical coefficient, and some people use it as 0.8. Then Mackay, he has so if you look at McCown's criteria, you get the breaker wave height as a function of just the breaker depth or nothing else. For example, if you are knowing at a certain location, this is a location where the wave is breaking, I am talking about the shallower waters. From that depth you can easily find out what could be the wave height at that point, which will be governed by this relationship. Mackay's criteria as early as 1944, he has given a relationship between wave height, water depth and of course breaking wavelength. So, this is another criteria which people use. The third one is Lamoite and Co. In 67, they obtained an expression in terms of deep water steepness, deep water wave height and beach slope. So, which formula you want to use? Apart from this, you have several other formulas. It depends on the kind of problem you are working on. So, if you want to have just a first hand information like for first approximation, you can use the first one without any problem, but if you want to account for the effect of beach slope and in case you have the deep water wave characteristics like your deep water wave height and the wave steepness, deep water wave height and the wave period, then probably you can use the third one, because this takes care of your B slope, that is m into m raised to 1 by 7. So the where you use the breaker depth and breaker height, all this information is what either you use it for evaluation of the wave forces due to breaking waves, or maybe it can be in the coastal engineering practice to estimate sediment transport, etc. So that is a different subject by itself, but you should know that there are formulas available. Apart from this, there are several other formulae, but I am restricting my discussion only in this only to this some of these 3 formulas. Having seen all these things, now let us understand some of what we have gone through on the topic wave deformation with a few problems. I will start with the most fundamental problem and try to show you the application of the different formulae, and that should give you a broader understanding of the subject what we are discussing about. Problem number 1, a 10-second wave wave having a height of about 5 meters here propagates from deep to shallow waters. The assumption here is the bottom depths are parallel to each other, something like a ramp. So this could be the most easiest problem you can think of. So this is only an assumption, so there can be loss or gain. If the bottom seabed is not even, if it is uneven, you can either have increase in energy or decrease in energy. So here we want to estimate the wave height in a water depth of 10 meters. So you already know how to calculate your wavelength. So calculate your deep water wavelength, come to d by L naught, then calculate using from the tables you can calculate d by L, and then calculate your wavelength, and also the deep water wave celerity in this case is 15.6 meters per second, and celerity from the earliest value you can, because the water depth is known, so you can from this relationship you can get the wavelength, and the wave celerity is L by T as we have seen earlier. So now we have the wavelength, and you can calculate the other parameters, and also all these parameters are needed in order to evaluate the factor n, which can also be taken from the tables directly, from the wave tables. Once this is known, you know what is the relationship, that is, since the bottom depths are parallel to each other, we are now considering only the phenomena of shoaling. So less of botheration, straight away use this equation which we have already proved by equating the power in the deep waters to the power in the shallow waters. So from this you get the ratio, the value for the ratio of H and deep water wave height. Is that clear? So here it is 0.98. Okay. So therefore the wave height in a water depth of 10 meters is now working out to 4.91 meters. What was the deep water wave height? 5 meters. Now this is what you get for this kind of a wave period and this kind of assumption of parallel water depth contours. Let us look at this problem. Herein the deep water wave height is 3.5 meters, the wave period is 10 seconds, and it is refracted so that the distance between the orthogonals is reduced by 50% in deep water, in a water depth of 10 meters, and reduced by 20% in 5 meters water depth. So what does this mean? This means that when the wave is, this is the shore, so when the wave is moving like this, so you see that this is the deep water distance between orthogonals. Here if you have about something like 10 meters and something 5 meters, so this is the B, the reduction is set to be 50%, something like that, okay. It is just an assumption. So here it is 20% reduction, 20% means 80% of the, this will be 80% of the B naught, this will be 50% of B naught. B naught is the distance between the orthogonals in the deep waters. Recollect again what we have seen under the topic wave refraction, okay. So as we have seen, we can change the problem also, like you can have divergence. If you practically do all these things, you will for a practical problem, if you apply the phenomena of refraction, as we have seen earlier, you can have either the orthogonals converging or orthogonals diverging. So here we have taken the case of convergence of orthogonals. What does that mean? Convergence of orthogonals means the wave energy should increase. Is that clear? So based on this, what is the solution for the, so what will be the wave height assuming no energy losses? So energy loss can be due to so many other factors. We are not considering diffraction here. There can be some amount of energy which is escaping in the lateral direction, okay. So in this case, what is the solution? What is the expression? H is equal to H by H naught equal to Ks, the product of Schelling coefficient and the refraction coefficient. And the Schelling coefficient, you have already have the expression as shown here, whereas refraction coefficient is the ratio of square root of the ratio of the spacing between orthogonals in deep waters to the spacing between the orthogonals in the shallow waters, any given water depth. So now as per the problem, it is clearly set, if this is B naught, there is a reduction of by about 50%. So B naught by B is going to be 2. So your refraction coefficient is square root of 2. So when B naught is then you calculate your other parameters, L naught, then D by L, then you know how to calculate your Ks as we have seen in the earlier problem. Is that clear? So now you have both your Schelling coefficient and the refraction coefficient, substitute and get the ratio between H and H naught. So you see that if this is the deep water wave height, if there is a convergence of the orthogonals, the wave height is going to increase compared to H naught. Is that clear? What was the deep water wave height? The deep water wave height was given as 3.5 meters. What is the wave height in now in 10 meters water depth? It is 4.86 meters, 4.86. So you have H naught as 3.5 meters. Now H is equal to 4.86 meters in a water depth of how much? In a water depth of 10 meters. Is that clear? The other thing what you have to check is, do we sometimes you have numbers, but you should also verify whether that numbers what you get is correct or not. So in this case, because all those values which we have taken for the problem, it is all assumed. I have assumed certain value for the deep water wave height. I have assumed that the ratio will be, the ratio between B naught and B will be of this value. So later we have to make sure that the assumptions are correct or not, it should not give some wrong results. There may be a situation that the orthogonals will never come close, this depends on so many other factors, for example the bathymetry etc. Okay. So in a water depth of 10 meters we have a wave height of 4.86 meters. What is the maximum wave height that can occur? That is equal to 0.78 times water depth, which is nothing but your breaker wave height. Breaker wave height is 0.78 times water depth, and here this water depth is 10 meters. So you can definitely have wave height of up to about 7.8 meters. So there can be a situation where the orthogonals can converge even much less than even what is indicated here. Okay. Suppose by having an assumption, and if you have a value much greater than this, that means this kind of a situation will not occur. Is that clear? So now we go into the next, so this is what is explained here. So this is what I have explained here, whereas the breaking wave height of HB of approximately 7.78 times water depth will be 7.8 meters. This is what I have explained here. For the above problem, suppose if the refraction is not considered, if the refraction is considered, the wave height is this much. If the refraction is not considered, then you see that your Schelling coefficient will be just less than 1, which means your wave height in 10 meters water depth will be less than the deep water wave height. Now is it clear? Wave can increase or decrease in shallow waters compared to its value in deep waters. It depends on the variation in the bathymetry. So earlier what we did not consider the bathymetry variation, we just considered that it is a slope. Here also if we do not consider the variation in the bathymetry, you see that the wave height in 10 meters water depth is less than the deep water wave height. Now the second the subdivision, the next subdivision in the same problem is wave height is equal to 5 meters, I mean in water depth of 5 meters, it is said that the ratio of B naught to B is 1 by 0.8. It is said 20% reduction. Okay. Is that clear? So that is what I explained in the beginning of the problem. So now you calculate this, this is your that is your Schelling coefficient, this is your Schelling coefficient, and this is your refraction coefficient. Now you look at the value is something like 4.34 meters. So will this happen? 4.34 meters, what is in that particular water depth, in this particular water depth of 5 meters, what would be the wave height, what could be the maximum wave height? 0.78 times water depth, that is equal to only 3.9 meters. But what are you getting here? You are getting a value 4.34, which is greater than 3.9 meters. So, this cannot occur. So, sometimes it is better to know the negative aspects so that you understand the subject more clearly. Is that clear? So, now you look at this effect. So, next, so the previous problem says that in the situations what we have seen, when you have a reduction by about 50% in 10 meters, there may not be a possibility of having further reduction within 5 meters, that is what it says. Okay. So, now the next problem is for a wave of 10 seconds period, h naught equal to 4 meters. Now, we will try to find out the variation of wave height when the wave approaches shallow waters from deep waters, and also determine the depth at which the wave would break theoretically. So, L naught can be calculated. Now, all these things we are trying to use this definition, which is the Minkes criteria, which we have seen earlier. So, later you will see when we examine this, we will see that the wave would break something around 5 meters. But the problem is, in the problem you have been asked to look at the variation of the wave height. So, now I take a water depth of 70 meters, I start from 70 meters. What is the criteria? The criteria is h by L, h by L is 0.1472 tan h kd. This is a well known criteria. Now, what does this indicate? So, we will use this. Now, try to arrive at the relation, the relationship on the right hand side and the left hand side with the help of this problem, wherein the water depth starts from 70 meters, and for 70 meters I have calculated d by L naught, d by L wavelength is calculated, then h by h naught is calculated, from which I can obtain h, and then h by L, and then this parameter which is on the right hand side. Which are you supposed to, which are the two which we are supposed to monitor? We are supposed to look at the variation of these two. So, all through you see that h by L is less than 0.142 tan h kd. So, this is less than this all the way until somewhere here you see that between 6 and 4 you see that this is less than this, but then this value increases that. So, that means the wave is going to break in between 4 and 6 meters. So, this is the problem which explains you the depth limited breaking, the criteria of depth limited breaking. Depth limited as well as your steepness also. Suppose in case you have only the deep water, then your tan h kd will not come into picture at all, only h by L will come into picture. Now, since the water depth is also included, I am calling it as depth limited as well as the steepness limited. Okay. Now, for the same problem, what I have shown here is the variation of your wave height from a water depth of 70 meters, and you see that there is a gradual decrease, and as you proceed towards the coast you see that there is a slight increase in the wave height, and somewhere close to the breaking condition the wave will break. And this figure, the right hand one, right side, the variation of the wavelength is shown for the above problem, that is, as you go towards the shore, the wavelength is going to decrease. So, these two phenomena we have examined in this. So, we will look at a final problem for today. So, for a wave of about 10 seconds, for a wave period 10 seconds, deep water wave height is given and beach slope is 1:15. Calculate the breaking wave height using various formula. Earlier we have seen about 3 formulae. Now, I will list some few formulae. I will not try to solve, because it is all just application of some simple formulae, but you will get the variation in the wave height predicted by some of these formulae. So, the first one is the Lamotte and Co. problem, which accounts for the variation in the beach slope as you can see here, and this predicts a value of 4.7 approximately for your breaking wave height, whereas the next below one, that is Komar and Gauguin, gives a value of about 4.2, and the other one is the third one is something like 5.3, then fourth one is 4.85, and finally the fifth one, Gauba and Schutter, gives you a value of about 4.8. If you see, there are several other formulas as stated earlier, mostly the values is around 4.8 to 5, something like that. So, for example, the second one looks slightly underestimating the breaking wave height. So, depending on the kind of wave you have, there are several other kinds of formulas for the breaking of estimating the breaking of waves. So, I think we have seen enough on the breaking of waves, and then in case you have any questions, you can ask me right now. So, if not, I assume that it is all clear for today. Thanks. Okay.